One of the most difficult concepts for early thinkers to get their heads around was the idea of nothing. Everywhere we go all our lives, there is something. There's air and matter that surrounds us everywhere because if there weren't, we wouldn't be here. Eventually, scientists and philosophers became comfortable with the idea of nothing and were able to study it. And what they found was that nothing was actually something. Learn more about vacuums and how the concept of it was accepted and then eventually created and put to use on this episode of Everything Everywhere Daily.
Want a website with unmatched power, speed, and control? Try Bluehost Cloud, the new web hosting plan from Bluehost, built for WordPress creators by WordPress experts. With 100% uptime, incredible load times, and 24/7 WordPress priority support, your site will be lightning fast with global reach. And with Bluehost Cloud, your sites can handle surges in traffic no matter how big. Plus, you automatically get daily backups and world-class security. Get started now at Bluehost.com.
This episode is sponsored by ButcherBox. I've told you before about my many forays into cooking with ButcherBox meats, and today I want to tell you about my latest adventure, meatloaf. I know meatloaf doesn't sound very sexy, but I've never made a meatloaf before, and it actually wasn't very hard. I took 2 pounds of ButcherBox ground beef, added 2 eggs, some chopped bacon, and some shredded cheese. I mixed it well, put it in a meatloaf container, and cooked it in my air fryer till it hit an internal temperature of 160 degrees. Came out great my first try. The center of the dish, of course, was ButcherBox ground beef. High-quality, grass-fed, grass-finished beef that was delivered directly to my door. And if you're interested in the highest quality beef, chicken, pork, and seafood, then you definitely need to check out ButcherBox. Sign up for ButcherBox today by going to butcherbox.com/daily and use code DAILY at checkout and enjoy your choice of bone-in chicken thighs, top sirloins, or salmon in every box for an entire year. Plus, get $30 off. Again, that's butcherbox.com/daily and use code DAILY. The TV show Seinfeld was often described as being a show about nothing. This episode is not like that. This episode is about something, and that something just happens to be nothing. In a previous episode, I covered the history of the number 0 and how early mathematicians and philosophers had difficulty coming to grips with the idea of 0. This episode is closely related, but slightly different. This is about the physical concept of nothing, which we know as a vacuum. The idea of a vacuum and the number 0 have very similar origins. Ancient Greek philosophers debated if a vacuum, which they also called a void, could even theoretically exist. Much of this was tied to the ancient debates about the existence of atoms, which I also covered on a previous episode. It was the Greek atomists, such as Leucippus, Democritus, and Epicurus, who were the first to introduce the concept of the void or a vacuum. According to them, if everything was made up of atoms, then there had to be spaces between the atoms, which consisted of nothing. Aristotle was one of the chief opponents to the idea of a vacuum, and he was the person who came up with the phrase, "nature abhors a vacuum." Aristotle's belief was that a vacuum couldn't exist because if it did exist, everything around it would instantly rush in to fill it. This is another one of those cases of ancient thinking being wrong, but also kind of being right. Given the circumstances that Aristotle was assuming, he was actually correct. A vacuum would be filled by the surrounding atmosphere if one were to instantly appear. This idea of a pressure and density gradient is behind many of the devices that we use today. However, Aristotle was ultimately wrong for reasons we'll see in a bit, and under circumstances he couldn't possibly have imagined. I should note that Aristotle's objection to a vacuum was different than the objection that many Greek philosophers had to the number 0. Aristotle gave a physical reason why he thought vacuums couldn't exist, not just a philosophical one. The legacy of Aristotle loomed large for centuries over generations of philosophers and scientists. During the medieval period, the Aristotelian viewpoint prevailed in both Islamic and European scholarly philosophy. However, some scholars, like the 14th century French philosopher Jean Buridan, began to question Aristotle's denial of the vacuum, proposing instead that voids could exist between the celestial spheres. Likewise, in the Islamic world, there was dissent from the orthodoxy of vacuums. The Iranian scholar El-Biruni said, quote, "There is no observable evidence that rules out the possibility of vacuum." Here again, Buridan and El-Biruni were right, but for reasons they couldn't possibly have known. One of the major debates amongst medieval philosophers was what happened when two metal plates were pulled apart from each other. The question they debated was if a vacuum existed after the plates were pulled apart, if even for an instant. Up until 1643, everything about vacuums was entirely theoretical. There were no actual attempts to create a vacuum, and no one even knew how you would go about doing it if you wanted to. There were some who felt that a vacuum was so impossible that even God himself couldn't make one. All of that changed with an experiment conducted by the Italian scientist Evangelista Torricelli. He performed one of the most iconic experiments in the history of science. He filled a long glass tube with mercury and inverted it into a dish also containing mercury. Torricelli observed that the mercury level dropped in the tube and stabilized at about 76 centimeters above the mercury in the dish, leaving an empty space at the top of the tube. This space, later termed Torricelli's vacuum, demonstrated that the space was a void of matter and that atmospheric pressure could support a column of mercury in a tube, challenging the prevailing Aristotelian belief that nature abhors a vacuum. Torricelli created the world's first barometer, but for the purposes of this episode, he also created the world's first vacuum. The French physicist Blaise Pascal duplicated Torricelli's experiments at different altitudes, confirming that a vacuum could be created. In 1650, the German inventor Otto von Guericke created the first vacuum pump, and in 1654, he conducted a famous experiment called the Magdeburg hemispheres. Von Guericke created two copper hemispheres, put them together, and pumped the air out inside to create a vacuum. Two horses then tried to pull the hemispheres apart and were unable to, and this was due to the power of atmospheric pressure. Robert Boyle, one of the founders of modern chemistry, conducted experiments using a vacuum pump he developed with Robert Hooke to study the properties of air and its mechanical qualities. His work laid foundational principles for the study of gases in a vacuum, leading to what would later be known as Boyle's Law, relating the pressure and volume of gases. Johannes Kepler in the early 17th century suspected that space beyond the Earth had to be a vacuum because of the lack of any sort of resistance impeding the movement of the planets. Now that a vacuum was no longer a theoretical question, it raised even more questions. One big question arose in the 19th century when researchers found that light behaved as a wave. As far as anybody knew, waves had to travel through a substance at the time. The ripples on the body of water had to have a body of water for the waves to propagate through. So, if light was a wave, what did it travel through? They initially thought that it was a substance called ether. Ether was believed to be an infinitely rigid substance that spanned the entire universe, including all the space between the stars. This theory was eventually disproven, and physicists accepted that light could travel through a vacuum. With the advent of quantum physics in the early 20th century, our knowledge of what a vacuum is became surprisingly complicated. So, what is our current knowledge of vacuums? For starters, the important thing is that there is no such thing as a perfect vacuum. A perfect vacuum is like trying to achieve absolute zero. You can come close, but you can never quite reach it. As you create a vacuum, it becomes exceedingly more difficult to remove the last few atoms or molecules of gas. The strength of a vacuum is measured in units of pressure, and there are a whole bunch of pressure units, including atmospheres, pounds per square inch, inches of mercury, millimeters of mercury, torr, and kilopascals. Torr is commonly used for vacuums, and 1 atmosphere is 760 torr. Technically, as there is no perfect vacuum, what a vacuum is a matter of degree. So anything below the surrounding pressure is considered to be at least a partial vacuum. There are vacuums that can be created on Earth that are extremely strong. However, these vacuums are extremely difficult to achieve. Once the pressure inside of a vacuum gets below 10 to the minus 9 torr, the gas molecules are so far apart that they are more likely to interact with the walls of the container than they are with other gas molecules. At that point, the gas molecules can't be pushed out of the vacuum chamber. You just have to wait for random gas molecules to find their way to the pump to be removed. These are known as ultra-high vacuums. There are also extreme high vacuums which achieve levels of 10 to the negative 12 torr. Laboratories involved in particle physics, like those operating particle accelerators, often strive to create these conditions to minimize the presence of any molecules that could interfere with the paths of accelerated particles. The most powerful vacuum ever created on Earth was approximately 10 to the negative 17 torr. There is a way to get much stronger vacuums, and that is by going to outer space. One question people often ask is, if space is a vacuum, then why isn't our atmosphere sucked into space? The answer has to do with gravity, and the fact that vacuums don't actually suck, high pressure areas push. Gas in our atmosphere wants to move into lower pressure areas, but it is eventually constrained by gravity. A gas molecule's ability to move further into the vacuum of space is always countered by gravity pulling it back down. As I've mentioned many times on this podcast, even space is not a perfect vacuum. In low Earth orbit, pressures are about 10 to the negative 6 to 10 to the negative 8 torr. In low Earth orbit, about 160 to 400 kilometers or 100 to 250 miles above the surface, about the altitude where the International Space Station flies, molecules of gas will collide with any object, slowly slowing it down. The friction caused by gases in low Earth orbit is enough that anything at that altitude will deorbit within about 5 years if measures aren't taken to boost its altitude. As you get further away from the Earth, the pressure decreases. In geosynchronous orbit, 35,786 kilometers or 22,236 miles from the surface, the pressure drops to 10 to the negative 10 torr. In interplanetary space, the space within our solar system, pressures are about 10 to the negative 12 torr. Finally, in interstellar space, the space between the stars in a galaxy, pressures are believed to be 10 to the negative 17 torr. And between galaxies, pressures are thought to be around 10 to the negative 18 torr, which is the equivalent of 1 hydrogen atom per cubic meter. And this would be as close to a perfect vacuum as you could find in nature. However, there turns out to be a lot more to it than the occasional hydrogen atoms. In the 20th century, quantum mechanics further complicated the concept of a vacuum, suggesting that even a perfect vacuum is filled with temporary virtual particles due to quantum fluctuations, leading to phenomena such as the Casimir effect. The Casimir effect is a quantum mechanical phenomenon where two uncharged, perfectly parallel metallic plates, placed very close together in a vacuum, attract each other due to quantum fluctuations. The effect predicted by the Dutch physicist Henrik Casimir in 1948 has been experimentally verified and is considered a striking illustration of the reality of quantum fluctuations in a vacuum. These quantum fluctuations that are found in vacuums are known as zero-point energy. What is tantalizing is that some scientists and science fiction authors have theorized that zero-point energy could be tapped as the ultimate source of energy. Now, we have absolutely no idea how to do this or if it is even possible to harness this, but if it were possible, it would literally be getting something from nothing. Because I know a lot of you are probably wondering what this all has to do with vacuum cleaners, I'm going to leave that topic for a future episode, as harnessing the power of partial vacuums and vacuum pumps for cleaning has been one of the biggest innovations in the 20th century. When the ancient philosophers debated the existence of vacuums over 2,000 years ago, both sides of the argument were sort of right, but in ways that neither of them realized. Yes, vacuums can exist, but they also don't exist insofar as there's no such thing as a perfect vacuum. However you choose to resolve their ancient debate, you do have to admit that they were the first people to have made a big deal out of nothing. The executive producer of Everything Everywhere Daily is Charles Daniel. The associate producers are Ben Long and Cameron Kiefer. Today's review comes from listener Chef Plain Pancake over on Apple Podcasts in the United States. They write, "The world's greatest podcast. Gary, I don't know how you do it, but keep doing whatever it is. You manage to make learning as easy as selecting a new recording and listening through. Additionally, do you know that when you listen to Everything Everywhere Daily, you get pure unbiased fact? It's the best podcast that I have ever listened to. Thank you for your contributions to learning." Well, thank you, Chef Plain Pancake. How I do it's pretty simple. I read a lot, I travel a lot, and every day I just sit down and crank out another episode. After the first 1,000 or so, it actually becomes routine. Remember, if you leave a review or send me a boostagram, you too can have it read on the show.